So, first of all, previous weeks we covered print, input, if, else, loops, lists, tuples, dictionaries, arithmetics. Are there any questions at all from any of the previous lectures? Let's go through them again just to be sure before we add today's topic. Today's topic is, by the way, going to be all around functions. Are there any questions?
No.
Okay, if anyone gets a question at any point, feel free to type it in the chat or say it. And yeah, let's start the idea. So first of all, let's go through with a high-level overview. So everything we went through in the previous weeks was happening straight away in our code. So it would be executed in the order that it was written. And that is generally fine, but sometimes we have repeating code. Sometimes we have code that maybe looks like the same 5 lines but with different variables, and we have to keep writing it over and over just to run it with different variables. For cases like that, Python, just like any other programming language, allows us to use functions. So functions are basically a grouping of lines of code so that they will all execute at the same time. For instance, and we'll get through the examples right now, but let's say there's some calculations that we need to do for each of the persons or each of the different situations. One way we were aggregating the logic before was to run it in a for loop and then run it for each person. But sometimes some logics don't allow us to directly run in a loop. So sometimes we might just need to call a function twice with different parameters. We'll see what this means in a moment. But basically, for intuition, here's what functions are. For instance, right now in our examples, we have used things like print, input, we have used converting to integers, we have used randoms, random function and the randint function. These are all functions, which just means that we write the circle brackets and inside them we put some arguments and they execute and they do something. Either they output to the screen or they give us some result which we then manipulate further. So today we'll start writing our own functions, and that will basically give us a higher level of toolset to get closer to doing anything. Now keep in mind, the idea with programming is that in principle, if you can figure out how to write a proper code for it, you should be able to do anything. So you should be able to, well, simple examples are to calculate some mathematical problems or model some physics simulations, or in our case, model some phenomena in the brain. You should also be able to understand by looking at the raw brain activity of a person what that person is thinking, what that person is feeling. Is the person calm? Is the person anxious? Maybe even read the person's motor activity and based on that control some robot hand so that the person can basically telepathically use a robot hand, which is very useful for paralyzed people, for instance, and all sorts of other creative uses that we can find. So basically, programming allows us to take action, both in terms of just calculating a number and returning it, or some kind of actions in the world. Now, the in the world kind of things will be covered more in our 6th week. But for now, let's discuss functions to, yeah, basically give us a higher level of ability to do things. Let's share the screen and we'll go through them now. So first, let's very quickly go through the examples of our previous lecture, just to make sure that everything here feels native before we move on to functions. So I'll just briefly cover this stuff. We had lists. So again, import random just allows us to call random functions, which are randint and random. Random giving a value from 0 to 1 and randint giving values from A to B, whatever A to B we give it. For instance, here we just print some text to the screen. We make a list of numbers, in this case spike times, and we put this list on the screen. we can add to the list, we can add a list to a list, we can remove the last element, we can remove an element with a specific value. We can also write an inline for loop. So this, as you remember, is actually equivalent to saying potential trace is empty loop, and then for nothing in range 100, potential trace append. So this is equivalent to this. Basically, this is just a way to shorten a for loop in one line. So we run through a for loop. In this case, we did not care about the index name. We could name it I, but when we don't care, it's common to just use underscore. And each time we go through a list from 0 to 99, create some random number from -70 to -50, and put it in this list. And then we say that from 20 to 25's region should be changed with these values. So basically, lists allow us to manipulate either a specific element or a sublist. So like in the 10 elements, you can manipulate the middle 3 elements to change them with other 3, for instance. What else do we have here? Yeah, we have just sublists. We can also take the last couple elements by saying minus and whatever. So -1 would give us the last element, -2 would give us the second last element, and so on. In this case, we would get -5th element and -4th and -3rd and -2nd and the last element as well, because this side is unbounded, which is basically same as saying whatever limit is. Here we go through the list, but we take every 10th element. This syntax is for where to start, and if you leave it empty, it will start from the beginning. Where to end, and if you leave it empty, it will end at the end. And what's the step size? So how many do we skip? And we skip over 10 at a time. Again, this -1 just means that we go through the list in reverse. So we start from the last element and end at the first element. Don't worry too much about memorizing this. They will come up again and again in homework, so it's fine. Just be aware that these tools exist. You can always look up the specific syntax, but you should know what you're looking for, basically. So again, we can have list of lists, or even list of lists, and so on. And in this case, for example, the element 1 would be just this list entirely. And element 2's element 1 would be just this number here. We can go through the lists by saying enumerate to get both the indexes and values at each index. We can go through them like this, or like this. They basically give the same effect, but this time we only get the values. This time we only get the indexes, but we can use the index to also get the values. And this time we get both the indexes and the values at the same time from a list. So far, is this clear?
Yeah.
Okay. Okay. If there's going to be a chat, I'll see. Yeah, so tuples were basically same as lists, but we create them with round brackets, and we cannot change their values. So you remember in lists, we could do things like this, right? Change the middle 5th values or add an element or remove. We can't do any of that in tuples. So tuples are just fixed size, fixed value. Whatever we create them as, that's what they stay as. They're basically an optimization, and also sometimes we want to constrain ourselves so that we don't accidentally make mistakes. So they're just a limited case of a list. That's pretty much all there is to say about them. But yeah, they're used in cases where we know nothing's going to change because they're a constant of some kind in our code. Also, we have dictionaries, which before lists were basically mapping an index, which is a number, to a value. So at element 0, they had some value, at element 1, they had some value, and so on. So like index 0, index 1, and then some value. But when we want to map them to strings instead of to numbers, so let's say we have an index of name, we have an index of location, and so on. In that case, we use a dictionary, and it looks like this. So now we would not say neuron 1 at 0. Instead, we would say neuron 1 at name. Neuron 1, like this. And we would get pyramidal cell, or neuron 1 at v rest, and we would get -65, and so on. So basically, a dictionary allows us to use strings instead of numbers as our keys. That's the main difference. And then we can find a bunch of uses for it. We can set an element, either adding or changing with the syntax of just at the index of this name equals this value. We can go through them. What else we have? We can go through the keys or the values. We can make changes. We can print the keys, print the values, and so on. We also had sets, which is again a list, but a list of unique values. So basically, in this case, for instance, right here, if we have this kind of list and we turn it into a set by saying set and then passing the list, what we will get is basically a new list that only has these values once. So GABA will only be included once, glutamate will only be included once, and so on. So it's just a way to make a unique list. And also for checking whether an element is in a set, sets work faster than just normal lists, because sets can use the fact that they are unique to sort themselves better. So you can ask, is GABA in this set? Is serotonin not in this set? We can create an empty set and then add values to it, and if we add the same value twice, nothing will happen. Basically, these are all the main ideas we covered last time, and I guess with these examples we sort of went through the loops as well. So now let's upgrade our toolset by introducing the functions. I'll start going through, we have 10 examples. Basically, let's go through them together. And if at any point you have any questions, feel free to ask me. But basically, the idea is we'll cover all these 10 different cases of how functions can be used, what they give us. And then, well, with homework, we will reiterate this knowledge. Okay, I'll start the function side now. Let's see. First of all, yeah, these are comments. They are ignored by the code, as we remember. But these are also comments, and they are also ignored by the code. So basically, this is a multi-line comment. So this is going to be ignored just as much as these are ignored. So remember this. But the difference is, this is used to document code. So whatever we write here is visible when we hover over some function. For example, here, we say that add adds two numbers and returns their sum, like return a plus b. Straightforward, right? But what's useful here is that if I hover my mouse over this add, I can see add two numbers and return the sum. Return the sum of that. They have to just to see that it changes. Yeah. See? So the point of writing a comment like this at the start of a function is that whatever you write there will be given as basically documentation. And this, what this allows us is that suppose a month later or maybe even days later, someone else has to use your code, or maybe you have to use your code, but you don't remember exactly why you made some specific function. You'd just look at this and you'd get the idea. I mean, in this case, it's pretty obvious. You add A and B. Obviously, you're going to just have A plus B. But for more complicated examples, it can be useful to have the documentation that tells you what it's doing. We could even have some very long description here, like the way this is done is explained by addition mathematics, so I won't explain it here. Or whatever level of complexity you want, and all of it will show up as a documentation, basically. Now, yeah, let's just simplify this. So let's cover all the new things that we see on this screen, and then suddenly you'll realize it's not in any way like difficult. So let's start with the basic example, greet. What does it do? It takes a name of a person and it returns a string that says hello name. So basically, if I say greet Nika, I will get a string that says hello Nika, and so on. In fact, that's what we do here. See, we say greet Nika, and it says hello Nika. But just to be completely clear, let's remove everything. In fact, let's comment out this area. And just with greet, let's just say, what happens if I say greet, I don't know, Alice? When I run this code, actually nothing happens. As you can see here, this does nothing because this doesn't directly write anything to the screen. Instead, it gives us a string value. We can put it in some variable like greeting equals greet Alice, and then we can print that to the screen. And then it will do something. Equivalently, we could directly print the result of this function to our screen. In this way, we would get it. So one thing to remember always is that in functions, you have a trade-off that you can either, whatever text you're writing here, you can either directly write it to the screen and not return anything, like this, in which case I would just say greet Alice. So it gets put on the screen. Or you can return a string, and then whoever uses this function will decide when to print it and when not to print it, basically. It's generally recommended to not put print statements directly in your functions because, for example, what if this function must be called by a website or by a game that doesn't want it printed to the screen but wants to put it somewhere else? Or what if this function is called by a place that also needs to add some other text to it? So for example, let's say that our greeting says greet Alice, but we also wanted to say welcome to our course and then print it to the screen. In this case, let's see it here. This way we would say, hello Alice, welcome to our course. But if I were to change this to just directly print it to the screen, I would not have as much flexibility anymore. That's the idea. So always try to prefer to only have a function that's only for printing to the screen and other functions only for calculating the result. It's generally best to not have one function both calculate a result and print to the screen, just because you want to keep the flexibility. All right, so here, again, we see a word called def. What does that mean? It means define. This is how we tell Python that whatever we write here is a function and should be callable. In fact, let's put a breakpoint in here so that we understand what this means. Let's run this code with a debugger, and we'll see exactly what's happening. So when our code first starts, it understands that there exists this function, but it doesn't go inside it. And then here we say that we call the function greet with the name of Alice. And so we enter here. Here we have a variable called name, we can see right here, and name is equal to Alice. And we calculate hello name, and we return that value, and we put it in greeting. And you can see in our greeting, we see greeting equals hello Alice. And then we can add this string to it. And here you can see now our greetings variable equals hello Alice, welcome to our course. And then we can print it to the screen. So this is the idea, right? So what did we do here? We defined a function, and if we didn't call it, by the way, nothing would happen. Like, if I don't call this function, it would be as if it doesn't exist. It never gets called, it never gets used. I could call it multiple times also. So I could say, like, let's see, one example of what we could do is we could say, for person in this list of people, we could greet each of them. Like, hello Alice, hello Bob, hello Charlie. As you can see, functions allow us some level of flexibility, but we'll understand with this other examples a little bit more about that. But the general idea is that with a function, we can give it some arguments and we can return some values. We could make a function that doesn't receive arguments, like let's say def greet everyone, but will just return hello everyone. So we could say, I'll print greet everyone. See, so we don't have to give arguments, but yes, generally functions require arguments, but it's not absolutely necessary. We might encounter functions that don't use arguments. We could also have functions that don't return anything but directly print to the screen. Like let's say draw a Christmas tree. Let's see if I can do it. Maybe like this, we can get a tree. Yep. If we do this, we don't get any arguments and we don't return anything, but we can still call this and it will still do something. Let's see, in fact, what it will do. I drew something like a Christmas tree. I can do it a little bit better, I suppose. Like that, maybe. It's kind of like an arrow, really, but yeah, whatever. Anyway, the point is we can have functions that don't receive any arguments or receive as many arguments as we want. We can also have functions that return a value or don't return anything and maybe instead print to the screen, or maybe even straight up don't do anything. So if we want our function to not do anything, we write here pass. And now, generally we do this if we want to write it later. So we might put a comment here that goes like to do, yeah, implement this later. And in this case, when I call this function, well, nothing will happen. Let's see. Here, nothing happens. Okay. So far, is everything clear?
Yep.
Okay.
Yes.
Good, good.
Yeah.
So basically def means that we create a function, we give it a name, we use that name to call this function. We can call it as many times as we want. We might have some arguments in this function, or we might not have any arguments. We might return a value, or we might not return anything, and we might just directly print to the screen or do nothing at all. Okay, with those pieces of knowledge in mind, let's move on to more useful examples. Let's say we want to add two numbers. And this is an obvious example, but suppose they might be more complicated things like two lists of numbers or something like that. But for now, let's go with just two numbers. What we could generally say at first, let's first do a simplified version of this. We could say def add a, b, return a plus b. And in this case, whatever we call here, like let's say c equals add 3 and 5. And if I print the c to the screen, yeah, basically it will be 8. Like that. Similarly, if I say 3 and minus 5, it will be minus 2 and so on. This is so far so good, but because our add function doesn't specify what kind of types of variables we want, someone might be confused and try to add, like, let's say 3 and some text. And this wouldn't work. This would give us an error because we can't add a number and a text. We can add a text and a text though. This way, actually, the code would work. Let's see. Because the two pieces of strings would be added to each other. Generally, Python is dynamically typed language, which means that we're not strictly controlled about when we use text and when we use numbers. But very often in real situations, we want to put those constraints on ourselves. So that is why we might say we want these variables to be numbers. Specifically, we want them to be floats. So we would say A must be a float and B must be a float. And further, we also want our result to be a float. So this is the syntax we would use. So this colon and then type just means that we expect this to be a float, we expect this to be a float, And this just suggests that we also expect the result to be a float. And this, basically what this does is that when we look inside our definition of our function, we will see that A is a float, B is a float, and the result is a float. Also, yeah, this comment that we put behind us. I mean, right here. Now, the thing is, this is not strictly enforced. So using strings on this will still work. Let's see. You can see it still works. But at least if someone looks at the function, they will see that it's supposed to be floats, and they will be able to consider this. In case I didn't write this code that I'm using, maybe someone else wrote the code and I'm just using it, or maybe I wrote it a long time ago and I don't remember. This kind of type hinting, it's called type hinting because you give a hint, but you can't really enforce it in Python. Yeah, it's very useful. If we really wanted to enforce it, we could say if A is not float or B is not float, we could raise an error, and this way our code would straight up crash. So this way we could say, because we are calling twist text, both arguments must be float, type error, our code would straight up crash. But generally we don't want to straight up crash, you instead just want to hint to people, hey, maybe you should use floats, or maybe you should use integers. Like you could put whatever you want in here, or maybe like this, if it makes sense. Yeah, so if you encounter this kind of code, it just means type hinting. And these are for what types each argument should take, and this is for what type the return value should take. Now remember, both the argument and the return value could also be a list, a tuple, a dictionary, a list of lists, a list of dictionaries of lists, whatever, any kind of complicated entity. So let's see what we have here. We have a function add, which takes A and B, both are supposed to be floats, and returns a float. And here the comment says add two numbers, return the sum that they have, I mean, obviously, and we return A plus B. Okay, so far so good. Now let's go with a little bit more complex example, not much more, but a little bit. Suppose we want to calculate the area of a circle. So from math, we know that the area of any circle is pi times the radius squared. So here we might say, give me the radius and give me pi. And yeah, I'll just say pi times radius times radius. This is the equivalent to saying this. But yeah, let's put it like this. Yeah, here we have a default value. Here's what this means. We know that pi is always 3.1415 something. And we might allow the user to give the value of pi explicitly in case the user wants even higher level of precision, or we can just leave them be. And let's see an example of what that means. We can ask, give me the area of a circle with a radius of 5, just like that, without specifying the pi. And it will still work because it will take this default value. In fact, let's see this in action with a debugger. Yeah, whatever. Let's go through the code. Here, when I say area circle of 5, we enter here. The value of r is 5, and the value of pi is initialized at whatever the default value was. So if I don't specify pi, it will just take this default value. It will calculate the result, and we see this printed to the screen. Similarly, then we can say area of a circle with a radius of 6, and let's say pi is this time 3.14 instead of being this precise. In fact, for a more exact comparison, let's take the same radius circles, and you can see what the difference is. Here, of course, we are not constraining this, so we could even say a completely wrong value for pi, like 3, or even just 15, which is way wrong, of course. But yeah, basically, what this allows us is to specify a default value for any variable. Now, of course, in the case of an area of a circle, we could also equivalently just not tell it here as well, and directly hardcode pi here to have this value always. Because maybe pi is an example where we don't want the users to specify it actually. So there is no constraint to having variables inside the function as well. This is completely fine, but these variables will only exist on the inside. Like if I ask what it is here, I won't get it because it doesn't exist here. As you can see right here, name pi is not defined because this pi only exists inside this function. There are ways to create global variables and use them inside as well, and we'll cover that right after our lecture is about to end. But yeah, basically, let's see if I can also get this in a moment. But we will rejoin on the same link once the meeting ends. Let's just uncomment this now. Wait this. And uncomment this. So, as I was saying last time, yes. Yes, Roa. Do you have a question? Or did you write one in chat? Let me see. No, I don't see anything in chat. Roa, do you have a question? I can't hear you. If you're having a question, maybe try typing in the chat.
Okay.
Okay, I can hear you now.
Can you hear me?
Yeah, I can hear you now.
I was saying that if we want to add any variable outside of the function, we can just write it at the top. Is this right?
You mean like this?
Yeah, like no.
What do
For
you mean?
example, for pi, we can just write it at the top of the code, or like to make it global variable.
Oh, yeah. Yes, we'll get to that in a second, but yeah, let me just show it right now. Suppose I defined my name all the way up here to be Nika. And here I want to greet myself. I can just do this and this will work. Not everyone anymore, but greet me, right? So if I do this,
Yes.
this will work. It will say, hello, Nika. So anything on the outside is already global and can be accessed by the inside of a function, but it doesn't work the other way around. Anything defined here, other name is, right, can't be accessed on the outside. Like we can't do this. That's the difference, basically. This is an error, but the other way around works. So this will work.
Okay, thank you.
Yeah. Now, a good question, and thanks for asking. And again, everyone, please feel free to ask questions. There might always be another student who also has the same question, is just being too shy, so you could be helping people. Okay, so just one more thing to cover is that, not one more, there's a couple more, but let's see. So previously, when we were saying that I want the area of a circle of, let's say, radius 5, I was saying it like this, area circle 5. This works, but another way to say it is I could say print area circle, and I know that the variable's name is r, so I could say r equals 5. And these two statements are exactly the same. So they are the equivalent. But if they're the same, why would we bother with this? The reason why we would bother with this is because what if we have optional variables? Or what if we have so many variables that the code is no longer understandable unless we give names? Let's give an example of that right here. Like, let's say we have describe person, and we take the name, which is a string, an age, which is an int, a hobby as a string, a city as a string, a country as a string, so on. And let's say we return a string as well. So we could just return this giant text. But what's important here is that if I try to now call this function, like print describe person, like this, I mean, in this case, we can figure out what each of these mean, maybe, but let's, for instance, make it different. Like say we also have a height centimeters. And maybe, I don't know, weight in kilograms, which is also an int. In this case, now suddenly, it's not very easily obvious if you look at this chart what each of these numbers are. Like, it's not very obvious just by looking here that this is age, this is height, and this is weight. We can still figuring that out by looking at this and then figuring out from here. But a much better way to do that would be to say print describe person and say name equals Bob, like this, basically. This is longer and we can put it on multiple lines to make it more visible, but this way it's much more clear what each of these numbers mean. Like here, we did not specify this, and it's you have to basically memorize that age goes first, then we have height, and then we have weight. But in this case, the names are right here and they just make things a lot more obvious. So sometimes if a function is complicated enough, like maybe it has many parameters or maybe it doesn't have many parameters, but it's not very clear what kind of parameters it needs. For example, let's say we have a temperature measuring function, but we don't want to just blindly trust that everyone will know to use Celsius instead of Fahrenheit. So we would say something like if measure temperature change. Let's say temperature in Celsius. And some function, I don't care what it does. The thing is, when we call it, just doing it like this would be dangerous because what if actually the person supplied this in Fahrenheit? But when you say temperature in Celsius equals 40, it's much more clear to the person that they must give Celsius instead of some other unit. Similarly with using meters instead of foot or using kilograms instead of pounds or whatever. Basically, to make sure that we don't get a difference because of units or because we don't know the exact order of these numbers or strings, it's very useful to say name equals age equals and so on when the function has these parameters. Now, one way to force that behavior is to use this kind of star symbol. And here's what that means. Right here, let's see what kind of function we have. We have a function that says summarize student. Let's only look at this, forget everything else. So this function will take the name of a student, let's ignore the star for now, the course that the student is taking, and whatever track the person is on right now. So the course and track are some text, and name is also text, and we say return, name is taking course, and the track is this. Now when I try to call this summarize student, I can pass the same one either like this or like name equals, either way will work. But after the star, anything that comes after the star, in this case here, any further ones will have to be specified by name exactly what they are. So I can't just say course 1, like track 1. This will not work. Because of a star, see, it crashes. Because it takes one positional argument but 3 arguments. Positional argument is just argument that we give straight away without specifying the name. So instead, I would be forced to say course equals this and track equals this. So basically, we can write a star to force people into using named variables when we are calling a function. So the star symbol forces us to use named variable for all following arguments. Arguments are same as parameters. Is this confusing?
No.
Okay.
No.
Okay, good. Let's keep going. So this is the basics of functions. Now let's dive into a little bit more. I realize we might not be able to cover all of it. I will still upload all of it, but I'm hoping we'll at least cover enough that it will be easy to go through the rest. Maybe restructure the rest as homework. Let's see how it goes. So there are two kinds of special arguments, let's say. In functions, we have stars and we have stars. Basically, star in name just means that this is going to be a list, and star name just means that this is going to be a dictionary, essentially. This is actually too much to cover at the same time, so let's start with a simple example of, let's say we want to find max among our numbers. And here we would say, let's say that biggest is just the first element of these numbers. And then for each of the numbers, we would say that if the number is more than our biggest, then our biggest becomes this number, and then we return the biggest. And now what this allows us to do is we can say print find max among, and just specify as many numbers as we want. So 1, 9, 3, 4, 7, 2, whatever, and it will find their maximum right here, 9. Don't mind this rest of the text, but yeah, it will say 9 right here. And if I add then 11, 12, whatever, it will also say 12. Now, how does this happen? Basically, behind the screens, this list of values that we didn't write as list, because we'll have to write it like this in order for it to be a list, right? But we didn't write it like that. We wrote it straight up as values. And this star numbers basically behind the scenes converts that into a list. So if I put a debugger here, you can see what I'm talking about. So by the time we come in here, okay, in this case, not list, but tuple, basically meaning that we can't change it. But yeah, these numbers here is a tuple with these values. So we did the equivalent of taking it like this, basically. And because of that, we are able to just comfortably add new values to a list. This is just one trick. You don't really need it because you could have always directly created a tuple and passed it. But yeah, it's just a trick that you might encounter in Python code sometimes. So if you say a star and then this, that's just what it means. You can even say something else first and then the list. Like we could say, maybe we will print the title and then do this. And in this case, let's see what this will do to us. Print, yeah, like this. We can see that the title was printed on the screen, and title in this case is this. And then the rest of the values were considered as members of a list. So in this case, we can have as many regular arguments as we want. And then after them will come a list, which is going to be just whatever is left. So this is one trick that exists in Python. And another trick is this one here, which is going to take all the named arguments that we give and turn them into a dictionary. So let's look at what that means right here. So in this case, we create a function called mix, which takes A and B. It also takes a list of values called more. And then after the list, we can still give named arguments, because if they're named, then you can tell that this is no longer part of the list. So for instance, we have one named argument that just says scale. And then we have this thing we call meta in this case, where basically you can see this one has 2 stars, which means that it will aggregate all the named values. So just before we get to that, let's have an isolated example of that right here. Type out values. So some A, B, and then values. And here we can see, let's just print A plus B to the screen, whatever. And then this values is a dictionary. So just like with any other dictionary, we can say here for key and value in values.items, just print them to the screen. And now I can say type out values, let's say 5, 10, and then whatever I want. So name is Nika, age is 22, city is Tbilisi, country is Georgia, and so on. And when I actually run this code, in fact, let's comment this out for now to not have any interference. when I run this code, you'll see that the sum of A and B were printed normally, like right here. And afterward, everything that we passed here was iterated through this dictionary, and we see them printed to the screen. So basically, the 2 stars will take all the named variables and turn them into a dictionary. Like, let me just show you very quickly. Right here, you can see our values is a dictionary with name equal to Niga, age equal to 22, city equal to Tbilisi, country equal to Georgia. Straight up from our code, yeah. Straight up from here, it was created, and we can always add new arguments. But of course, again, we could have just created a dictionary ourselves right here called values dict and supplied all of this directly in here. And we would have to do it like a little bit differently, but it would work like this, and then like this, and so on, and this would work. I'm a little bit lazy to do this right now, but okay, fine, I'll do it. 1 second. So this would be the equivalent of passing it like this. We could just then pass this value instead. But yeah, basically this allows us to create a dictionary straight up on the fly with all the named variables that we have. And they can be combined like this. Might be a little bit confusing example, but we have some variable A, some variable B, then some list of values, and then a scale and some list of named values again. And in this case, what happens here is that we count the total as A plus B plus the sum of whatever was passed in the list. We multiply it by a scale, and then we find a note. Note just means that in this dictionary, we see if there's any key called note, and if there is, we'll get whatever its value is, and if it isn't there, then we'll get the default value of no note. So let's see what that means right here. Let me just point this out. Let's see this code run. Why was this printed anyway? So when this code runs, you can see right here, we wrote total is, and in this case, it was just these numbers. So 1, 2, 3, 4, and multiplied by a scale of 0.5. And you can also see note demo call with unpacking. What does unpacking mean? Let's consider this for a second. We could have said here that the first argument A is just 1, second argument B is just 2, and then some more nums would be 3 and a 4th list. So we could then say unpack some more nums, or even just directly say 3 and 4. If I did this, like mix 1, 2, 3, 4, and called this function, the way this would work is that we would see that A became 1, B became 2, and these other ones, 3 and 4, were put inside the more. You can see here, more is 3 and 4. Then the next one, scale, became 0.5. You can see here. And the meta, in this case, we passed a note value. So meta, it became just a dictionary that has a key of note with a value of demo call with unpacking. I'm throwing a lot of concepts at you right now. Don't worry too much about this. A lot of this is not completely necessary in everyday coding kind of situations, but we still need to be exposed to them, so to speak. Let me just run through this code. Yeah. So, and then we could also similarly call it directly on some by unpacking a dictionary. Unpacking a dictionary like this with 2 stars and options would be the equivalent of saying scale equals 2.0, note equals from 2 to 0. So this and this, let me just not call that at all. This is same as this. So these two lines are doing the exact same thing. We could unpack a dictionary and just get like these ones, or just write it directly. Exactly the same thing. All right, so we covered a way to directly pass a list into a function with star, a way to directly pass a dictionary by saying this equals that equals, and similarly we can unpack a list or we can unpack a dictionary. To unpack a list means to say instead of 1, 2, 3, 4, we could have said like this, and it would do the exact same thing. It would register them as 4 separate variables being passed to this function. All right. Let's move on now to more useful topics, so to speak, because these are still just tricks that are used here and there, but they're not quite as important as the things that we are about to cover. So let's just take a moment of break, and let's continue. All right, so again, if you have any questions at all, interrupt me at any moment. I'll check the chat every few minutes, but yeah. If anyone gets a question, interrupt me. Okay, let's go into the next one. Scope and mutability. This is where we cover more what goes local, meaning only exists inside the function, and what goes global, meaning it exists for everyone. So we'll cover local versus global scope, mutable, default, anti-pattern, and the fix. So suppose I have a variable at the top here called counter. Let me just comment out everything else for now. And in this counter, if I want to increment the counter, if I say this counter plus equals 1, it actually won't change. So if I do this, and then I call it right here, like you can see, in fact, what the counter's value was before. Say before and after. Not only did nothing happen, but in fact, we got an error because it's a local variable counter referenced before assignment. So this counter could not change this one. It thought it must be a different value, but we can't increment it if it doesn't exist yet, was the complaint. Okay, then let's see if we can directly set the value of it. Like, let's see if instead we can say def set counter to 10 or to some x, and we'll give this x, and we'll say counter equals x. Here, let's say set counter to x, and we pass 10. You would think that maybe this would actually change this counter to 10, but it won't. See, it was 0 and remained 0. The reason for this is because even though these are called by the same names, by default in Python, whatever variable is declared with equal sign inside the function is going to have its local scope. So this counter is different from this counter. So whatever changes we put on this one now won't affect this one. And if we want to affect this one, what we could do is, of course, one way would be to just return our value and then directly do it here like this. Of course, that's one way. But to actually change it inside, what we can do is we can say global counter. And this will tell this function to use the global value of the counter. Now this will work. Now if I say set counter to 10, before it was 0, but after it became 10. So global is a keyword that lets us access this. And to be clear, we only need to write this when we are changing the value. If we were only reading the value, we would not need it. Let's see an example of that. Right here, we can say, let's comment this out, def display counter, which just prints the counter to the screen. Counter value is and counter. And if I say display counter right here, this will work just fine. Let's say the counter is 4. You can see this works without a problem. So Python can already tell global variables. They can already see them. It just can't change them unless we say global counter. So if you don't care about changing them, you can still use them directly. But yeah, if you want to change them, you have to say global counter and then do whatever manipulations you want on it, including assigning, incrementing, or whatever else. Let me just uncomment these ones as well. It's fine. This shouldn't crash. No, it doesn't. So this is what global allows us. Now let's see what other tools we can see. So this is again touch global, which just means that in order to increase the counter by 1, we first have to get global access to it. Now let's see what else we can do. What is here? Push value bad. Mutable default persists across calls. Here, let's see the difference between this. In fact, that is displayed quite nicely here. So let's just go through this. Let me just now remove this and let's only look at what's going on here. So we have two kinds of push value, as you can see, functions defined. And basically, both of them take a bucket, which is supposedly a list of numbers, and they both add the value of x. But there is a difference between them. And let's see what that will look like. So right here we see, if you want to push a value, we might have some list of nums that already have some values, and we might push it straight to this one. And in this case, it will just add the 10 to our list just fine, as you can see. But what's the problem with this? The problem is if we give it a default value of an empty list, it has a strange behavior that this actually persists across calls. So this is honestly a bug that Python shouldn't have. Like this honestly should not exist in Python. But unfortunately, that's how Python is set up. So let's see exactly what this means. What this means is that, let's comment out this part. Right here, when I call push value bad without giving it a list, it will create an empty list. In fact, let's put our breakpoints here. And so this time, when it returns a bucket, it should be a list with only the element 42, right? And this time when I call it again, since I'm again calling it without specifying the list, it should again give an empty list. But instead of giving an empty list, here's what it will do. The second time, it will give us both the 42 and 99. And basically, to quickly see the reason for this, let's run it with a debugger. And you can see here, first time we came in here, the bucket is an empty list. And we add to it, and bucket now has 42. Now the second time we go into it, the bucket already has the 42. So even though Python was hi Anna, to uncomment everything you can mark all the lines you want and write Control/. So Control/. On Mac it might be Command/, but yeah, basically that's how you both comment and uncomment everything. Yeah, just Control/ to do that. Okay, so the easy way to fix this is to have a default of no list and then creating the empty list inside it. So if we do it the good way, right here, we won't get that error. Like here you can see the 42 was not preserved for the second one because the list was created inside the function. So this is just some strange problem that Python has, and we just have to be aware of it. Okay, now let's go to one of the most important themes of functions, which is recursion. So first of all, any problem that we have that involves going through a list or doing steps multiple times can be done either by iteration or by recursion. Every problem we did so far was by iteration. Now, in a moment, we'll see what the difference is. Suppose we want to calculate a factorial of a number. Like generally, we know that the factorial of like 6 is 6 times 5 times 4 times 3 times 2 times 1. And similarly, the factorial of any n is n times n minus 1 times n minus 2 times and so on times 2 times 1. There are two ways we can think about this. One way is that the iterative way of thinking about this is we go through numbers from 1 to n and multiply them. So like we can say that if our n is 10, factorial can just be, let's say, 1 at first, and then for I in range from 1 to n plus 1, just to cover it as well, we can say factorial times equals I. And this would give us a factorial of 10, whatever it is. Let me just calculate. So if we run this, we'll see that apparently this is the factorial of 10. Let's give it a small number so that we can verify it. Yes, the factorial of 4 is 24. So this is one way to do it, which is to go from 1 to n and multiply them all. And the other way to think about a factorial is that n factorial is really n times n minus 1 factorial. This is called recursion, because we would be calling the factorial upon itself until it goes down to some base case of like n equals 1. In fact, let's write that ourselves. So let's do the factorial recursive version right here. So we have n, which is an integer, and returns an integer. We will say, first let's say that this will just be n times the factorial recursive of n minus 1. Now the problem here is that this will never stop calling even after n becomes 0, minus 1, and so on. So we would need a base case to make sure that this doesn't go on infinitely. So for base case, let's just say if n equals 1 or n equals 0, let's say that the answer is 1. And just like that, we can also say factorial recursive of 4. And it will also give the correct answer. Or of 5, and it will also give the correct answer, and so on. So basically, almost any problem can be solved by either iteration, which means going through a loop, or recursion, which means doing one operation, like in this case, multiplying by n, and then repeating the same function with a different parameter. So in this case, n factorial is equal to n times n minus 1 factorial, which is of course equal to n minus 1 times n minus 2 factorial, and so on, all the way until we go down to a number like n equals 1 or n equals 0, let's say here. So that then it will end. If we didn't write this, by the way, this function would never stop calling. And maximum recursion depth would be exceeded and our code would crash. Yeah, so these are the main two ways to do anything, iteration or recursion, and we'll cover them more. So here you can see just iterative version. We can also, basically protect us by saying you can't use a negative number. So there will be an error if you use a negative number. Result is 1. And let's go through the numbers and multiply them. Or similarly, we can say if it's 0 or 1, return 1, or otherwise return n times factorial of n minus 1. Similarly, we can get a list of numbers, a sum of a list of numbers, by either saying total equals 0, let's go through each one and increase the total. Or we could say we can break down the list of numbers into a head and tail, which basically just means the first element and the entire rest of the list. And we can say the result is this first element plus this sum function called on the rest of it. And this can keep going forever until it goes to the end. So this will actually do the exact same thing as this. Now, actually, I want to cover one more small example before our meeting ends. Actually, you know what? Let's rejoin after this meeting ends as well for just 10 minutes. And I'll quickly cover the main parts of the rest of the concepts. And then we'll end our today's lecture. Okay, let's just quickly cover the next theme as well. So the next theme right now is, and by the way, if I'm going too fast, interrupt me at any moment, and I will recover the same subject basically. So let's not worry too much about this right now. Let's suppose we want to calculate the Fibonacci number. So as you recall, the Fibonacci is basically this pattern where you have two numbers, and then there's some, like these two sum, then these two sum is next, then these two sum is next, then these two sum is next, and so on. Now there are a few ways to think about what the Fibonacci number is. Like, let's say this is the first Fibonacci number, the second, third, fourth, fifth, sixth, and so on, right? This is eighth Fibonacci number, ninth Fibonacci number, tenth, and so on. And really, you can say that Fibonacci number at place n is really equal to the sum of the previous two Fibonacci numbers. So one thing that we could do is we could say that so one way to define this Fibonacci function, the naive way, which means just the simple way, Fibonacci naive, would be to just say if n is 1 or n is 2, just return 1 because that's the result for the first two. And otherwise, just return Fibonacci naive of n minus 1 plus Fibonacci naive of n minus 2. And this works. Like if let me just comment this out here. If I ask it for Fibonacci naive, so as I was saying, basically, this will work. This will always give us the correct result. But the problem is, if we want to calculate the Fibonacci value of a very large number, let me just run this. This will work, right? In fact, let's see, for index 8, we indeed get 21. For index 10, we indeed get 55, and so on. But if we want, let's say, 100th Fibonacci number, the code is still running. Like even as I'm talking to you, the code says still not finished running, because this is going to take a really long time. I'm not sure if actually it will run in a few seconds or a few hours even, but I'll just explain why it takes so long and what we can do about it. Basically, consider this. What we are telling it right here is that to calculate let's see, what are we asking naive Fibonacci? Naive Fib, right? Let's call it Fib. It's just shorter that way for now. What we really ask is that we say Fib n equals Fib n minus 1 plus n minus 2, right? But similarly, Fib n minus 1 is Fib n minus 2 plus Fib n minus 3. And Fib n minus 2 is Fib n minus 3 plus Fib n minus 4. And Fib n minus 3 is this and so on, right? And thing is, if you notice, the exact same values have to be recalculated over and over again. So for instance, this value has to be calculated twice. This value will have to be calculated even more times. And so on, because like when we counted what the Fibonacci value of 3 was, or Fibonacci value of 5 was, we did not remember it anywhere. And so now, every time a new number has to calculate it, they have to recalculate it. And because of that, the amount of calculations we have to do doubles for each step. But this is unnecessary. What we could do is we could remember the value at each point. This is actually automatically solved for us if we do Fibonacci iteratively. Like, let's just do that quickly. If we do Fibonacci iteratively, we would say that we have an A and B that we start with, which is, let's say, 1 and 1. And for I in range, starting from the index of 3, I guess, to the index of all the way to n plus 1, every time we would say A and B becomes B and A plus B. And then in the end, we would return B. And this would always give us the correct answer, just like this one gave. But this time, our code would not crash. Our code would not take a million years. Let's just verify it with some low number like 5, which we know the answer must be 120. Sorry, the answer must be 5. And for 8, we know the answer must be like 21, and it's here. And if I ask what is the Fibonacci value of 100, it quickly calculated this giant value. The reason why it quickly calculated is because this will happen in linear time. So because this is going through one for loop of the size n, twice as big n will take twice as more time, but just one more n will just take one more calculation, which is fine. The reason for this is because we are building this up from the ground up. We could do similar thing in our recursive Fibonacci if we simply bring a way to save our results. Now, how could we save results? For example, let's say we have a dictionary of Fibonacci's, call it fibdict, whatever, which is empty at first. And what I would say here is we could say, if we have already remembered the value of Fibonacci at n, if n at fibdict, then just return that value. Otherwise, calculate it, let's say result equals this, and put this in our dictionary, and then return the result. And because of this, any single values Fibonacci will only be counted once. And so now let's say this is fib with memoization. This is called memoization, by the way. Memoization kind of, honestly, maybe should be called memorization. You can think of it, but yeah, it's basically the same thing. And fib naive, let's say, is the version of this that goes directly like this. If n is 1 or 4, to return 1, otherwise return this, right? So let's see the differences here. As you remember, if I call fib naive on 100, it takes forever. Now this is actually from this one. So this will take forever because I'm calling it on the naive implementation. But if I now call it on fib with memoization, it will quickly execute. So these are just some of the tricks that we use. These are called algorithms. And algorithms are just basically tricks we use to make our code either require less time or less space. Space just means how many variables we have to use, so that how much room we need on our disk or on our RAM. And time is, well, yeah, basically, do we have to wait 1 second or 1 year for the code to run? So yeah, memoization basically makes it, gives it a linear time complexity, which means that twice as big input would only take twice as much time. Whereas for this code, every time the input increases by 1, the amount of time it needs doubles pretty much. So yeah, this is just one useful trick. We might dive into this at the end, but it's not our main focus. I just wanted to mention it. This is called memoization. Yeah. And here we have another way to do that, which Python actually gives us. It's called LRU cache, least recently used cache. Basically, let's see what this does. So functools is a library that includes this function called LRU cache. Let's see what it does. So right here, here's what it does. This is it. So you remember before, right? We had the same logic, but we said LRU cache at the top, and now Python will remember the values for certain inputs. So right here, fib naive takes forever, right? But if we put LRU cache on top of it, with max size of none so that it can store any size, now if I call fib naive of 100, it will work just fine. Because now Python will take care of remembering what the value of this, what the output of this function was for the given input n. So this is equivalent to this. Okay, is this clear?
Yes, it is.
Yes.
Okay, Good.
I got it, yeah.
Okay, nice. We might cover a little bit of algorithms in our next lecture as well if we have time. But yeah, basically this is just an introduction to it. Just one more algorithm I want to mention is one that's very common, and it's called binary search. And there are a couple ways to do it, but in fact, let's recreate it right now together to get the idea of what it is and why it's useful. Suppose we have a list of numbers, like so. But it has to be a sorted list. So it's increasing list, basically, like this. And suppose I want to know if some element, like some x target, let's say, in this case 50, I want to know if this target is in the list, and if so, at what index. So just to be clear, this is index 0, 1, 2, right, like this. So we could say find target index, and I would say this is my numbers and this is my target. A naive way to do this would be to say for I in range of length of numbers, if the number at this point is equal to target, then our answer is 1, this index, and if it never finds it, then the answer must be -1. And we can just say here, print find target index for our nums and target. This should give us 3, right? And it gives us 3. And if I say some non-existent number like 500, you can see that it gives us -1. So this works. But the problem is, if my list was the size of 10 billion, I would have to check all 10 billion of them one by one. Now, a better way to handle this is to, let's just make it a little bit bigger list. Like this, let's just make it a huge list. Now, a better way to handle this would be to use what's called a binary search. The idea of binary search is that, let me just write out the indexes of these ones as well. Yeah. Oh, it does have some spatial awareness. That's cool. So the idea of binary search is that because this list is already sorted, at each point, like let's say our target is, yeah, 500 is fine, I guess, but let's bring it to 80. What we can do instead of checking one by one, because as the list gets bigger, that will take too much time. Instead, at each point, we can check just the middle of the list. Like in this case, the middle would be, I guess, like maybe here. And we can say, if this element is bigger than our target, then for sure anything to the right to it is also no good to us, and we would forget everything to the right, and then only care about this side of the list. Then here, similarly, we would also check the middle, like for example, maybe that middle is this. I mean, if it's this, then obviously the search is over, but let's say if the middle is considered this, then this is also more than our target's value, so this and everything right to it would also be deleted. And we would only care about these ones. Now again, we would check the middle, which is this, which is less than our target. So we would delete this and everything to the left of it. And we're left with these ones. And we keep going. And so at each step, we basically take away half of the possible values. And we check the middle of the remaining half until eventually we find our target. Now, the way to do that, let's do it quickly here, is like this. Binary search, nums and target. Here's what we can say. We can say that we have the left end, which is at first 0, and the right end, which is at first just the last index of this, for example, in this case, 17. So while left is less than right, here's what we can do. We can say that the middle that we want to check is just left plus right divided by 2. And if at middle we find our target, then that's it. And otherwise, we either cut the left side by bringing the left to just one path to the middle, or we cut the right side. And then in the end, we will say if left equals right and nums at left equals target, return left. Otherwise, return -1. So let's see how this would work. First of all, let's check that it indeed works. Let's say I want to find 80 in this list, so it should give us the index of 4. And yeah, it gives us index 4. And if I ask for something that doesn't exist, like 85, it should give us the index of -1. Yeah, that works. Now, to see how this works, let's just pick some value like 203. Right here. And let's run it with a debugger to see what's going on. So we enter here. We have our list of numbers. And we have our target, which is 203, right? So at first, our left and right here you can see our indexes in this list at 0 and 17. So at the first time we come in here, our midpoint is going to be index 8. At index 8 we have 207, which is of course more than our 203. So we will see here that we come right here, and because it's more, we know that none of these are any good, and so the rightest that could be correct should actually now become this point's -1, so 7. So because of that, right here we say right equals mid -1, and just like that, now we only care about the list from 0 to 7. So basically now we only care about this range. Now in this range again, we come in, we take the middle element, which is at the value 3, so this one, which we now check and it's less than our target. And so we push our left to the one side, right to it. And now we have left of 4 and right of 7. So now we only check in this range. So just like that, we brought it down this much. We check it again and so on until we converge on the correct answer. And now only one left is this place because we explored every other place. And we will see that it is equal. And then we will return that left. And just like that, we got our answer that it's at the index of 7, this 203. This is a useful algorithm called binary search, which is very good for finding basically if an element is in a list, but it only works if the list is sorted. Because if the list was not in our increasing or decreasing order, then knowing that the midpoint was less than or more than it would not have any meaning. So I'll just throw this. This can be done with recursion or with iteration, like I did. But yeah, both options are fine. I will just throw this example of code in our Discord chat as well. It's just something to keep in mind. Now let me just quickly close in on what else we had here. So let's say we have a dictionary called brain, which includes cortex, which is another dictionary of parts, and then another dictionary and sub-dictionaries and so on. And say we want to flatten this. A flattening means either for a dictionary or a list to make this 1D. So for basically what that means is, let's go with the lists example first. If I have numbers like this, flattened version of this thing would be just 1, 2, 3, 4, 5, 6. So this is a list of numbers, but actually these are the elements of this list. And then this one is a sublist that actually also has a list at one element. And then one element is also a sublist. So this is a list of lists of numbers. But if we were to flatten this, it would become just a regular list of numbers. That's what flattening means. A lot of the times our data will be complicated, especially brainwave data for neuroscience. And it will be very useful if we can flatten it into a normal list so that we can just take one loop through it. Because right now, if I was to take a loop through this, first element would give me 1, second element would give me this entire list, and third element would again give me 6, which is very messy. So it would be very useful to be able to flatten a list into this. And similarly, we might also want to flatten a dictionary of dictionaries into just one super dictionary. So here, let's see what it would mean to flatten either a list or a tuple. So basically, what we would do is we would say, let's say that the flat version is an empty list. We go through each item in this nested list, in this case. And if it's a regular item, like if it's a 1, we would directly add it to the list. And otherwise, we will call the flatten on this list now. and whatever list it comes up with, we will add that list to this list. And this is one way to flatten a list. And this is a way to basically flatten a dictionary. You can look through it. But basically the idea is that a lot of the times if you have a list of lists, it's very useful to change it into just a regular list. This is the idea with flattening, and it can be done with, most easily it can be done with recursion. So this is an example where recursion is quite useful. So basically you would keep calling the flatten until, for as long as whatever you get here is also a list. And if it's an element, you just add it. Okay, just one more thing I want to explain. These other ones we'll cover in the next lecture because we're going too much over it, our limit. But yeah, let's just quickly cover lambdas, just basically introduce them. So this is just a regular list of dictionaries, like nothing crazy. But here we introduce a new idea. We introduce the idea of a lambda. A lambda is an inline function. So previously we saw an inline for loop, right? So we saw that a sum of numbers, or like let's say a squares of lists. Let me just give an example. If we have some numbers, 1, 2, 3, 4, a simple way to create a squares of them would be to just say like this, x times x. But another way would be to just say squares equals x times x for x in nums. So this is an inline for loop, which will just go through each number, call it x, and then calculate x times x, and make a list of those. And this is the exact same thing but written out. Similarly, there exists a lambda function. A lambda function is a function that we can create inline. For example, let's say we have a function that give a square of x and returns x times x. And similarly, we can say square giver is lambda of x that gives x times x. Let me just fix this. Okay, I'm not sure what VS Code is telling me right now, but basically there exist functions for which we can call lambda like that to define a list, define a function right in place. In this case, this is what it gave. So let's see what that means. Let's see what this does here. Like what this does is it created this n of and takes some ID and whatever. Like this could have been a function extract stuff from n, which returns this. And here I could have said extract stuff from n. Okay, it's messing up for no reason now. Okay, I'm not sure why this code is crashing, but yeah, basically the idea with lambda is that we create a function in place. Like let's say right here, this is a function, a lambda function, that will receive an n, which is in this case some dictionary, and if it will take the value at the key called spikes, and if which is apparently a list in our case, like right here you can see this is our dictionary. Each specific one is a dictionary. It has spikes, which is a list of numbers, and it will see if that list of numbers size is more than or equal to 3. So in this case, this is a filter, which is a function that comes from Python, which will basically only keep the values in the list which allow that to be the truth. So in this case, in our neurons, the first one and the third one would be kept because they have at least 3 elements in their spikes list, but the second one would be removed. That's what filter does. So there exists a filter, there exists a map, and there exists these things that we can do to manipulate. And here you can see a squaring function is just lambda of x, which gives x times x. And now we can say, and then lambda is like a function, we can call it like a function. So basically lambda is an inline function. We'll cover it more deeply in the next lecture, more properly. But yeah, I want you to take a look through this code and also this code and this code for which we don't have enough time right now, but these are just examples of things that we already covered. Okay, our lecture was a bit long today, but with that, we've covered all the stuff I wanted to cover. Now, do you have any questions?
No.
Okay,
No.
No,
okay, that's good. I will upload all
thank
the
you.
code that we covered today, and I'll send the homework as well. Okay, see you next week.
Okay, thank you.
Bye.
Thank you
See
so
you.
much. Bye.